Okay, so first of all, I lied. I said we were going to look at DE tools next. And when I went to enter our equations into DE tools, I realized that with a negative 20 in our matrix, it was bigger than DE tools wanted to deal with. And so I was able to enter in the nonlinear system, but DE tools wasn't giving a very clear picture of that. So I will simply tell you that we classified the equilibrium point as negative 1/2 5 as probably being a spiral source, and it is. Okay, it's not as perfect a spiral source when it's nonlinear as it is when it's a linear system. So the spiraling around that point might be a little more convoluted, et cetera, et cetera. But it will behave essentially like a spiral sink. Now, that's not to say that this method of linearization always works, but it most of the time does. Okay, we will talk in a later video about when it doesn't work, but I want to take a look at another time when it does. Okay, so I've got the same nonlinear system up on the board. We had determined that this had 4 equilibrium points. 0, 3 was another one, so I just want to work with that. So we're going to be creating this new system, U prime V prime equals this matrix, which is going to be our Jacobian matrix times UV. And U is just going to be x minus 0, so it's just x. V is y minus 3. And what that's doing is that's taking this point in the xy plane and it's associating it with the origin, 0, 0, in the UV plane. Okay. Now, the entries of this Jacobian matrix are just our partial derivatives. So it's the partial derivative of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y, and all of this needs to be evaluated at the point 0, 3, because I don't want functions as my entries, I want numbers as my entries. Okay. But essentially, this equation, this function f, was giving us our x values. Those derivatives go in my first row. The function that was giving me my y prime values, sorry, not x prime, the function that was giving me my y prime values goes in the second row, and then we always just go in alphabetical order, x and then y. Okay. All right, so let's go ahead and calculate those. So the partial derivative of f with respect to x, now we've done this before, but let's do it again. That's 4 minus 4x minus y. So the partial of f with respect to x evaluated at this new point, 0, 3, is going to be 4 minus 0 minus 3. That's also 1. Okay, so we're going to have a 1 here. The partial of f with respect to y, on the other hand, was just negative x. So the partial of f with respect to y, evaluated at 0, 3, is just going to be 0. So now we've got a 0 at that point. All right, if I calculate the partial of g, you know what, I'm just going to clear myself some space. If I calculate the partial of g with respect to x, we said that was just negative 4y. So the partial of g with respect to x at 0, 3 is going to be negative 12. The partial of g with respect to y is 3 minus 2y minus 4x. So the partial of g with respect to y at 0, 3 is 3 minus 6 is negative 3 minus 0 is still negative 3. So there's our linear system, linearized system. Okay. U prime V prime is equal to this matrix times UV. Okay. That's approximating the behavior of this nonlinear system at and near this point. I know at this point we have an equilibrium solution. This point gets translated to the origin, which is the equilibrium solution here. I'm going to now classify the equilibrium solution here, and in most cases, this equilibrium solution will behave in the same way. If it's a sink, it's a sink. If it's a source, it's a source. If it's a saddle, it's a saddle. So let's take a look. You'll notice I didn't say if it's a center, it's a center. That's going to be a problem case for us. Okay, so if I look at this, J minus lambda I would be the matrix 1 minus lambda 0, negative 12, negative 3 minus lambda. So the determinant of J minus lambda I is going to be 1 minus lambda, negative 3 minus lambda, minus 0. So that's just lambda squared plus 3 lambda plus lambda is plus 4 lambda minus 3. My characteristic equation is lambda squared plus 4 lambda minus 3 is equal to 0. Okay. Looks like that does not factor, so we'll solve for it. Lambda is going to be the opposite of 4 plus or minus the square root of 16 minus 4 times 1 times negative 3 is going to be plus 12 all over 2. So I get negative 4 plus or minus the square root of 28 over 2. Notice that's going to be negative 4 plus or minus 2 root 7 over 2. And if I factor out a 2 and cancel, I'm going to get negative 2 plus or minus root 7. So I have two real eigenvalues here. I can see for sure one of them is negative. Negative 2 minus root 7 is going to be negative. Now if I look at negative 2 plus root 7, well, root 7 squared is 7. And 2 squared is only 4. So root 7 is bigger than 2. So here, the positive part would win. So this is a saddle. So I know that in the UV plane, the origin is a saddle. And now I'm making an educated guess that in the XY plane, 0, 3 is a saddle as well. And in fact, that educated guess is right. So what's kind of interesting is if I were to look in the XY plane, I know at negative 1/2, 5, we had a spiral sink. At 0, 3, we have a saddle. Okay. Now, that only classifies what happens near these points. So if I get close enough to this point, I'm going to start spiraling around and approaching that point. I'm not going to get super close to this point because since that behaves like a saddle, if I started coming in towards this point, I'd then turn away from it. That suggests I might see something like this, a curve that started coming in, no, turned away, got dragged into this, and did something like that. Now, I'm not claiming that that's accurate. I'm just saying that that's the sort of thing we could have if we had a saddle here and we had a spiral sink here. We need some additional tools in order to be able to actually see what happens at other places. But this is a very, very useful tool for classifying our equilibrium solutions. Okay. And I guess I can actually talk in this video about when it doesn't work. Okay. So it works if we have a sink, and that would include a spiral sink. If we have a source, and that would include a spiral source. Or if we have a saddle. If, when we come up with the linearized system, we classify our equilibrium point there, we can classify the equilibrium point in the nonlinear system the exact same way. So when doesn't it work? It doesn't work if we get a center. And that kind of makes sense because a center, remember, was sort of the boundary between having a spiral sink and a spiral source. And just a slight tweak to the system could change things from being a center to a spiral source or a spiral sink. But it's possible to tweak the system in such a way that you get the same linear approximation for multiple systems. Okay. So if the linearized system has a center, we can say that the nonlinear system will exhibit some circling behavior, but we won't know whether that's actually acting as a center or a spiral source or a spiral sink. Because all we know is that it's close to the boundary between spiral sources and spiral sinks. And if you're close to the boundary, that doesn't tell me which side you're on or whether you're exactly on the boundary. So it doesn't work in that case, and it doesn't work if 0 is an eigenvalue. Now, if you remember, in the linear system, when 0 was an eigenvalue, that meant that we had an entire line, or possibly the entire plane of equilibrium solutions. When that was the case, we didn't bother even in the linear system to classify the origin, because it wasn't the unique equilibrium solution, and it really wasn't special in the way that the unique equilibrium solution is. So these are the two cases where it doesn't work. You would just say, I'm able to linearize, I linearized, I got this. It doesn't tell me what the equilibrium point in the nonlinear system does. But if you get any of these in your linear system, you can say, yep, that's what I'm going to have in the nonlinear system. And that just means it doesn't describe the entire phase portrait, but it does describe, if you were to zoom in on just the part of the phase portrait right around that equilibrium solution, the behavior you'd see would be the behavior that you saw in the corresponding linear system. Pretty cool.